Okay, this is going on page 93 when we're done. I'm not going to read all these words to you. I'm going to read you kind of the first part, then we'll talk about the rest as we go. But so far, we've learned to define sine and cosine values for angles in standard position, how to measure angles in radians, how to use the unit circle, and we're going to put all this kind of stuff together so we can understand how to represent sine and cosine functions graphically. Okay? Now, have we already looked at it kind of graphically? Yes, because this circle is a graph, okay? This circle here, our unit circle that is so pretty and we love so much, it is on the x and y coordinate plane. It is a graph. Is it a function as you know a function? No, because it fails the vertical line test, right? So not really a function. But it's also what's called a parametric curve. And we haven't talked about parametric equations yet. You don't have to know anything about them right now, and that's fine. But before we move on to another type of graphing, you need to understand how different this is. We are used to, when we graph, we have an x value, and we substitute it in, then we get a y value. And so this is why we say that y is a function of x, right? We have an input, we have an output. But here, these ordered pairs, this is cosine theta, sine theta. X is not my input. I do not input cosine to get sine, right? That doesn't make any sense. My input is theta. So my x value is a function of theta, and my y value is a function of theta. Does that make sense? So technically we have three variables. We have x, y, and theta. That make sense? Where here we just have x and y, okay? Now, again, we don't have to completely understand the whole parametric idea of things. What I want you to understand right now is that it's different. That's the main thing. And to understand that when we're looking at the unit circle and we have these ordered pairs, x and y are both functions, okay? And then we'll worry about parametric stuff later, because we're going to actually graph things in graphing terms that we are already comfortable with. We are going to split the unit circle, basically, and unroll it so that instead of having cosine and sine as my x and y values, my x value is going to be theta, my y value is going to be sine of theta. And when we do that, cosine is nowhere around. So we're going to have an input-output situation like we're used to. My input is theta, my output is sine of theta. Okay? We okay with that? And so again, at the beginning, the things we have to, there's some confusion and misconceptions that happen when we start graphing like this. But I think it's gonna, hopefully I can make you understand at the beginning, if you can keep them separate in your brain, there's something else I'm gonna have you keep separate, and they are related. I mean, they come from each other, that's why they exist, but you don't want to think of them as the same type of thing, because that's when the confusion starts. So let's start by just filling out this chart, because we can do this without worrying about graphing at all. My input's theta, my output's sine. So what is the sine of pi sixths? 1/2. Thank you. I know I'm asking you very hard questions. What is the sine of pi thirds? Square root of 3 over 2. Good. Pi halves? That's pi fourths. But that's okay. That happens all the time. 1. Okay. 2 pi thirds? Square root of 3 over 2. 5 pi sixths? 1/2. Pi? 0. All right. 7 pi sixths? Negative 1/2. Good, because we're down in the third quadrant, right? So 4 pi thirds, square root of 3 over 2. Good. Negative 1. 5 pi thirds. Good. Square root of 3 over 2. Good. 11 pi sixths, negative 1/2. And 2 pi, 0. Here's the other thing you need to keep separate in your mind, is that you've known what the quadrants are for a long, long time, right? But until we started talking about this trig stuff, you probably hadn't really thought or talked much about the quadrants, right? And then we've been talking about them all the time with the unit circle. And it is important that we know this is quadrant 1, this is quadrant 2, this is quadrant 3, this is quadrant 4. That is true whether or not there's a unit circle on here, right? That's how the quadrants on the coordinate plane work. When we are talking about the quadrants as we go through this, we are talking about the quadrants of the unit circle. Look at the grid that we have to the right here. Which quadrants show up right there? 1 and 4. But guess what? We don't care. So even if I'm looking at this graph and I'm asking you about an angle, because notice over here, your x-axis right here has the angles on it. Yes? So when I ask you what quadrant is 7 pi 6 in, it has nothing to do with the quadrants on this graph and everything to do with the quadrants on this graph. You with me on that? So quadrants, when you're thinking quadrants, you are seeing the unit circle. Don't worry about we don't care what quadrant number we're in over there. Okay? Does that make sense? And I think those two things, understanding that the functions act differently and that we're only, when we talk about quadrants, don't worry about looking over here. We're looking here. And then I think that that'll kind of help, hopefully, clear up some confusion before, well, not clear it up. Hopefully it'll never happen. So let's plot these points here. One of the points that is not on the chart is 0. What is the sign of 0? 0. Okay? Sign of 0 is 0. Oh, well, it would help if I actually had a pen. So I'm going to plot 0, 0. Then I'm going to plot this point right here. When theta is pi halves, sine is 1/2. Pi halves, no, it's not, pi 6. When sine is pi 6, I'm at 1/2. I'm going to plot that point. When theta is pi thirds, sine is square root of 3/2. That's about 0.866. Not a number you really have to know, but you need to know it to be able to plot it right now. When theta is pi halves, we're at 1. Then 2 pi thirds, I'm back to square root of 3/2. So go ahead and go through and plot these points. Good observations. No crying. No crying in math. You can cry in physics. You can't cry in math. I'm sorry. All right. So we see the wave, right? Which might make you think of physics. Hopefully it does not make you cry. Okay. But one of the things we left off this chart was pi fourths. And we can put it on there. We'd have more points, but we don't necessarily need to be able to see what is happening here and see this curve. Now, as I go from 0 to 2 pi, just like when I make a full rotation around the circle, then I just kind of start over. That's what's going to happen on this graph as well. It's just going to start over. So I want to show you a little animation, basically of kind of what we just did. And make this connection for you, hopefully. So here on the left, we have a unit circle, okay? And on the right, we have the grid that we just did. Now, and I'm going to talk about quadrants again, but I'm talking about my unit circle right here. So I'm starting here at 0. I'm going to go to 1 or pi fourths in the first quadrant. This orange little line that you see here is the same as this. That is my vertical displacement. That is my y value on my unit circle. Make sense? So I am going from sine of 0 is 0 to sine of pi halves is 1. And that's the radius of the circle, so that's going to be my maximum. I'm not going to get any higher than that, right? Then my y values start decreasing again. But look, sine, we know sine is positive in the second quadrant. Because between pi halves and pi, it's still positive over there, how we understand positive. Make sense? Then when I go to the third quadrant, from pi to 3 pi halves, I know sine is negative, and that's why on the right-hand side over there, we're below the x-axis. Then from 3 pi halves to 2 pi, I'm here, and then I just start all over again. And it just keeps repeating. Okay? And that's what's happening there. Okay? Does that make sense? Okay. Good deal. All right. So we are here. Now, we're not going to connect these dots because your dots look pretty good, and you've got a connected one right there, so we don't want to mess up our pretty dots. Okay? Because I know mine would look like a hot mess, and that's fine. So we have this. This is showing you one cycle of sine. It is what we consider the parent function for sine. So we have f of theta equals sine of theta, or it could be f of x equals sine of x. You could see it either way, and it's fine. So we have one cycle going from 0 to 2 pi. Then some of the vocabulary here. Midline, that word came up the other day, and I said, we hadn't talked about midline yet, but it means it's in the middle, and there's half the definition, and it is. So my midline, it's halfway between the maximum and minimum values. So that midline is right here. When we graph these, the midline is something we graph in like an asymptote. It's not actually part of the graph, but it helps us greatly with everything else, okay? The midline, if my graph shifts up or down, the midline goes with it. If it shifts left or right, it doesn't go with it because it's shifting left and right. But it is a line, so midline, so it's always a y equals because it'll always be horizontal. So it has to be written as an equation because it is a line. Okay, we okay with that? All right, so then we have amplitude, which is the A in our transformations. It's the same A as in any transformation. It's your vertical dilation, right? It could be a stretch or a compression. So for what it is on this graph, it's the distance from the midline to the maximum or minimum. So this distance right here, this is your amplitude. For the parent function, it's 1. So if I had 2 sine of theta, my amplitude would be 2, so I'd have a vertical stretch, and my maximum would be at 2, and my minimum would be at -2. So it's the same stretch compression thing that's happening there. Okay, you having some light bulbs go off for physics? Hey, good for you. Okay. Then we have the period. Now, we talked about periodic functions the other day. The period is how long it takes to go through one cycle. So again, we're going from 0 to 2 pi, just like on the unit circle for sine, for the parent function. So the period is 2 pi. The frequency, we'll talk more later about what frequency means. Right now, I just want you to know how to find it. Frequency is just the reciprocal of the period. So if the period's 2 pi, frequency is 1 over 2 pi. Okay? And the graph of the sine of theta oscillates between concave up and down. So this wave thing that's happening, that's what's oscillating. It's kind of going back and forth. But we're oscillating between concave down and concave up. So from here to pi, I'm concave down. Then it's concave up, and then it just keeps repeating. Where else have you heard amplitude besides here and physics? Music, exactly. Sound waves. You ever seen sound waves? Right? Sound waves look kind of like this, right? And maybe goes up and maybe goes down, something like that, right? And so the amplitude of sound, if this, when your sound increases, your amplitude increases. It's all related. Okay? They are your sound waves, those are sine waves. Okay? That's what those are. Do it. Good job. I care. That's good. See, it's a connection there. All right. Any questions at this point? All right. So before we flip it over, when we start to graph these, and we're going to graph in the midline and stuff, the parent function, sketching a parent function is always super important, even when we're not graphing, and I'm going to tell you why. So here's when I say, what does sine look like? The picture that you need in your head for the parent function and what you need to be able to sketch quickly is just this. That's it. Okay? That's the parent function for sine. And look at how else it can help you. When I ask y'all for sine or cosine of 0, sometimes I get crickets. Okay? And maybe it's just an extra second, but it's because you're thinking, like, where's that ordered pair? Is it x or y? But look at this graph. When theta is 0, sine is 0. Like, these graphs can help you with that as well. And so at 0, at pi, and at 2 pi, sine is 0 for all of those. Okay, so having that visual might be helpful too. And again, different people latch on to different things to make sense in your head, but you still have to have this picture regardless. Okay? We good? Questions? All right, let's flip it over. So now I'm going to remind you that in the unit circle, this is cosine theta, sine theta. Right? That's our ordered pairs. We've already talked about we've already talked about sine. We are going to do cosine here. So this ordered pair is theta, cosine theta. Now, one of the confusing parts sometimes for people are like, the y value of what we're about to do is the cosine value. But here, it is the x value. But that's because these are two totally different type of graphs, right? For a unit circle, it is still the x value, always. But that's because x and y are both functions. Here, my input is theta, my output is only cosine. We're not talking about sine right now. Okay? We okay with that? All right, so let's fill in this chart. What is the cosine of pi 6? Square root of 3 over 2. Yeah. Okay, and then pi thirds? 1/2. All right, so y'all go ahead and finish this chart on your own, because you got this. I know you do. but I did fill it out wrong in one period because I wasn't paying attention, so might want to double check me. Okay, we got our chart filled out. Almost. Double check it. Then one of the things that is missing from the chart is 0. What is the cosine of 0? 1. So at 0, I'm going to go to 1. At pi 6, that's the square root of 3 over 2, which is about 0.866. And then go ahead and plot the rest of the points. Is that kind of what you expected? All right, so now I want you to think. So you're looking at your cosine. I'm going to flip back to sine. Don't flip yours over because I want you to be able to look at them both at the same time. So you have your cosine in front of you. Here's what we had gotten for sine. Do they look similar to each other? Well, they're not. I don't mean the same. They're not exactly the same. Do they have some things in common? Yes. Is there something that I could do to this sine function I have in front of me to make it look like the cosine? I could translate it. I could translate it to the left pi halves, right? And then would it look like what you have? Could I also translate it to the right some? I'd have to translate it more, but because it keeps going in either directions, I can translate it. Or I can translate the cosine one and get sine, right? This is why this is called sinusoidal functions. There's no such thing as cosinusoidal functions. Because cosine, if cosine didn't exist, all of these equations we could write in terms of sine. We still need cosine. He's still important for reasons. But that's why sine waves, your sound waves, are sine waves. They're all considered sine waves, even if it is a cosine function. Okay? All right, so let's flip back. We're here, right? Let's talk about our properties of cosine. We've got the midline again. It's still halfway. Whoops. We're still halfway between the maximum and the minimum. So that's right here. Still a line, so y equals 0, right? All right, so your amplitude, which apparently David got right on his physics test. Your amplitude is right here. It's the distance from the midline to a max or a min, or another way to look at it, remember, is half the distance from the maximum to the minimum, because we might need to look at it that way. And that is your A value when you do your transformations, right? Period, we still went from 0 to 2 pi for one cycle. Frequency is still just the reciprocal. We'll talk again more about what it is later. And again, this one oscillates between concave down to concave up and vice versa. So let's look at cosine here. All right, so remember, this is my unit circle. This is my other x and y coordinates. When we talk about the quadrants, do we care about the quadrants over here? No, we care about the quadrants over here. So this is cosine, right? I'm going to start here. I know that what is the cosine of 0? 1, and that's why this blue line is right here. So where we were looking at the orange line on the other one, we're looking at the blue line here, okay? So as I go through the first quadrant and I get to pi halves, everything's positive in the first quadrant, right? Okay, so then we know that cosine is negative in the second quadrant. Right now, cosine 0, because my little blue line, my horizontal displacement is 0 right here, yes? So then I go through, as I get to pi, all of my cosine values are negative, and I know that the cosine of pi is -1, right? That's my minimum. Cosine stays negative in the third quadrant because what's positive? Tangent, good. So tangent's positive in the third quadrant, but then cosine's positive in the fourth quadrant, and that's where those distances are coming from. My x values are positive, my x values are negative, my x values are negative, my x values are positive in my unit circle. Okay? Does that make sense to you? All of these x values are positive, all of them, because they're all those angles we're going from 0 to 2 pi. But on my unit circle, x value is positive, x value is negative, x value is negative, x value is positive. Okay, and that's my cosine curve. We good on that? Okay. So let's go back over here. And for when we are sketching these, the picture I want you to have in your head for the parent function of cosine looks like this. And just like with sine, this can help you with your function values and help you remember them. Okay, because you can either look at the ordered pairs and visualize that in your head as you go around the unit circle, or if you know that this is what cosine looks like, the cosine of 0 shouldn't stump you because you know you're starting up here at 1. Okay, we okay with that? What questions you got? All right, so then down here real quick before we get to the examples, this is what I was talking about with your sinusoidal functions. Everything's a sine wave. No such thing as a cosine wave. There's cosine graphs, but all the waves for sound and stuff are sine. So a sinusoidal function, any function that involves additive and multiplicative transformations of sine of theta. Therefore, sine and cosine functions are both sinusoidal functions because of this translation that we talked about. Okay? What questions you got? Perfect. I'll take that as none. So grab your other sheet of paper. Let's look at some examples. 93. Yeah, this is going to go on 93 also. So two periods of the sinusoidal function f of theta are shown in the figure above. Find the period, frequency, amplitude, and midline for the graph of f of theta. All right, so the period is pi, right? So let's think about this. I could start here, and if I go through one cycle, I could end here. Yes? Could I start here and end here? Yes. But which one's easier to figure out, pink or green? Pink, for sure. So you don't always have to start at 0, but if you can, it makes it a little bit easier. But sometimes you don't want to start at 0 because maybe it's weird, like whatever it is. But yeah, I'm going from here to here, so the period is pi. So what is the frequency? 1 over pi, yes. A sleepy 1 over pi. Midline. No. Midline is in the middle, remember? 3. But it's not just 3, it is, I heard some, y equals 3. Very good. Amplitude is 3, yes, because it is the distance between here. So the amplitude is 3. Okay, we good on that? All right, what questions we got? Okay. So then we're here. Several periods of the sinusoidal function g of theta are shown above. We're going to do this one together too. I was going to give you time, but I feel like I'm afraid I'm going to run out of time. So we'll just kind of do this together. Can I start here? Okay, if I start here, where do I end? The top of the next one, right? So that means my period is pi over 2. Good. Yeah, and then the frequency is 2 over pi. Now, I heard earlier today 1 over pi halves. That's a true statement too. But if you're taking a reciprocal and you have a fraction, just flip it over. Like, don't make it complicated. All right, so where do we think the midline is? All right, so if this is 3, this is -1, I'm here. So yes, y equals 1. So then what is the amplitude? 2. Good. What questions we got? Yeah, the next one's there's no graph. So let me show you how we're going, because with the graph, if we understand that, we can do this, all right? This tells me that we have a sinusoidal function, has a maximum at this point, the first minimum, all right? So think about this. There's an infinite amount of minimums, right? But if I have a maximum, the first minimum I come to, meaning like the next one, that kind of tells me spacing, after reaching that is at this point. And then I want to find all this stuff. So we're going to sketch some stuff. We're not sketching the whole thing. We don't need to. We just need some key pieces of stuff. I want to get these points on there. So my x values, I have a pi and a 3 pi. I don't even really care how accurate things are. I just need them labeled so I can figure stuff out. My y values, I got one at 8 and one at -2. That looks good to me. Okay. So my first point, which is pi 8, would be here. And my second point they gave me, which is 3 pi -2, would be here, which is inside my 3, but that's totally fine. Okay. Everybody with me so far? Now, remember, these could be sine or cosine graphs. I have no idea, and it doesn't even matter. But if I think about this being where I start, because I really don't have a place, like I don't know where I'm starting. No, it's not really starting anywhere. I'm actually starting at the maximum. Which function starts at the maximum, sine or cosine? Cosine. So that means I want this little picture in my head, or actually written down for me, because that could be helpful. If this is cosine, and see, mine's not even accurate. That didn't even really go down as far as it should. But this, I'm at a maximum, is where I start. At 3 pi, I'm at a minimum. So if I'm just doing this part of the graph, how much of the period is that? From here to here? Half, right? I only went half the thing. So from pi to 3 pi, that's only half my period. From pi to 2 pi, that distance is what? 2 pi. So I don't know what came out of my mouth, but from pi to 3 pi, that distance is 2 pi. That's only half of that. That means my period is actually 4 pi. But do you see how this is just half of it, right? And the nice thing about these is everything is half, half, half. So from here to here, then this is the middle, then this is the middle of that, and whatnot. So what's the frequency? 1 over 4 pi. Good. So now we want to look at the midline. It's in the middle of the graph that I'm not even going to draw the graph over to the right, because I'm afraid if I do, it's just going to be so wrong, I might confuse myself. I didn't need it, right? I just needed an idea of what's happening. But halfway between 8 and -2, that's the average, right? So if we average stuff, we add them and divide by 2. So 8 plus a -2 is 6. Divide by 2, you get 3. So my midline here is at y equals 3. Now, I heard somebody say 5, and I've heard 5 all day. The distance between this and this is 10. And half that distance is 5, but that's not the midline. That's this, which is what? The amplitude. This distance is 5, and this distance is 5. That's the amplitude. Okay? So you see the difference between that? Because if I put my midline at 5, then it'd be 3 away right here and more away down there, and that's not actually in the middle, right? And that's another reason why if you at least draw that out, if you put the 5 there, you'd be like, that doesn't even make sense, even if I'm not to scale. Like, it just won't make sense to you. Okay? What questions you got? We good? All right, flip it over. Now, we are revisiting this question that we did last week. So I'm going to go through the first part quickly because we kind of already did it. Oh, my goodness. All right. So we have an 8-inch long moving minute hand. This right here, 8 inches. Okay. Then the center of the clock is 120 inches directly above the ground. This is 120. Maybe it'll make more sense to you this time. You won't be as stressed out. Okay. At time t equals 0 minutes, the hand is pointed directly up right here. However, the clock is not working properly. It's moving twice as fast. So then the next time it's up at the 12 is t equals 30. The next time it's right here. So at 0, when t is 0, we are the maximum distance from the ground. What is that distance? 128. 30 minutes later, when my t-value is 30, I'm in the same place, which is 128. Everybody okay with that? That makes sense? Okay. So then it says, as the minute hand moves, the distance between the endpoint of the minute hand and the floor periodically decreases and increases. So remember here, the distance is decreasing, then increasing, then decreasing, then increasing, and it just keeps on going and going and going, right? So let's look at this graph, because this is the same graph. The questions after it are different. But it does tell me to come up with the possible coordinates. Well, I know when time at t equals 0, I'm 128 inches from the floor, and that's the maximum value. So it's got to be one of these two. But since I have 2 points I want to get on there, I think it needs to be this one. So we're going to go with 0, 128, which means this one is at 30, 128. Because these are sine and cosine waves, they are, or are functions rather, they are evenly spaced. Everything is half, half, half. So halfway between these 2 points, halfway between these two x values would be this x value, which would be 15. We'll figure out why here in just a second. This one right here, g, it's halfway between these two x values. Now, last time we did this, we used decimals, but I told you on most of the other ones that look like this that we're going to go through, you're probably going to want to keep them as fractions. It'll just make your life easier. So we'll just go ahead and leave this as 15 over 2, which means this ordered pair, what would this x value be? What's halfway between j and p for that x value? How do you find halfway? If you have a piece of string and I want to find the middle, I'm going to take the two ends, put them together, and divide it in half like that, right? So I'm going to take this and this, put them together, get 45, divide it in half. It's 45 over 2. Okay, that makes sense? Think about a piece of string. That's what we're doing there. It's just averaging. It's nothing complicated. Okay. Now, if this is my maximum, this is my minimum. So my minimum distance from the ground would be here. When the minute hand is here, what is that distance? 112. Good. So this is 112. And just like for the x values, the y values are evenly spaced also. So what's halfway between 128 and 112? 120. Which makes this 120. Okay? Everybody okay with that? All right. So now, period, frequency, amplitude, midline. What is the period? Well, first of all, do we get the period from x or y? X. Okay, so what is the period here before we start to repeat? 30. Yes, good. 30. So this would be 30 inches. No. Is it inches? Yes, okay. It's okay that it doesn't have a pi in it because it's different units, right? Frequency, what would the frequency be? 1 over 30, exactly. Amplitude. Is amplitude x or y? Y. So we're looking at this right here, right? What is that? That's the y. What's that? 8. From 112 to 120 or from 120 to 128? The amplitude is 8, yeah. And then the midline. Midline is a y equals, I just heard that. Y equals what? What does y equal right here? 120. Do what? Okay, I know. That's why I'm asking you. You should ask yourself, is what is this coming from, x or y? If we're going vertically, that's y. If we're going horizontally, that's x. All right, so this next part says, find find two intervals for which the graph of h is both decreasing and concave up. So we are decreasing and concave up right here, right? So that is, and on the intervals, they're always intervals of the domain, so it's x. So we're going from 15 halves to 15. Does that happen again? Do we have the values for that? We don't. I mean, we can find them, but that's happening here, right? So let's start with just the x values, or whatever. What is the x value for this one? What would it have to be? If I'm 0 here, 15 here, 30 here, this would be 45. Good. And what's the y value? 112. Okay. And then here, what would my x value be? Right here at this point. 75 over 2. Very good. And what's your y value? 120. Do we actually care about the y values to answer this question? No, but we can figure them out, so it's fine. So then that interval goes from 75 over 2 to 45. Okay? What questions do you have? Anything? No, because we only have 4 minutes left, sorry. All right. Yes, there's one right up there on the board.